Hi everyone, this is Babaiah, Assistant Professor of EC Department, MLR IT, Hyderabad. Today I am going to explain or derive the expressions of the time domain specifications. Continuation part. Previous way some expressions are derived time domain specifications like rise time as well as peak time, right? Now, but today I am going to derive the more expressions for the time domain specifications like maximum overshoot or peak overshoot, and as well as the settling time. These two are I'm going to derive the expressions of the time domain specifications. Now let's move on to the first here, peak overshoot or maximum peak overshoot. Just to derive the expression for the time domain specification. All the time domain specifications are involved in a underdamped second order system for unit step input, right? Just we consider the underdamped second order system response, that is the c of t equals to, that is c of t is equals to 1 minus c power of minus zeta omega nt divided by under root 1 minus zeta square and sine of omega dt plus theta, omega dt plus theta. This is the underdamped second order system response. Further, now we are going to derive the maximum overshoot or peak overshoot, right? The percentage peak overshoot or maximum overshoot is equals to the the ratio of the peak response to the maximum response or final response, maximum peak value to the final value. Just the definition is the ratio of difference between the ratio of maximum peak value to the final value is known as the peak overshoot or maximum peak overshoot. For percentage of the peak overshoot or maximum peak overshoot, just to multiply with the 100%, multiply with 100 for that peak overshoot or maximum overshoot, where c suffix tp is nothing but the peak response, that t equals to tp, and c of infinity is nothing but the final steady state value. The unit step response of the second order system is given by c of t equals to 1 minus e power of minus zeta omega nt by under root 1 minus zeta square sine omega dt plus theta. Just I am writing here. Already I mentioned this one here. This is the underdamped second order system for unit step input response is c of t. Right here, two condition. We need to calculate the c of tp or peak response for tp equals to t condition and t equals to infinity condition. T equals to tp and t equals to infinity condition we are going to calculate. Then only finally we got the maximum overshoot or else peak overshoot expression, right? See here, first let us say consider as at t equals to infinity, that is the final steady state value, right? So t equal to infinity, for that condition c of t equals to c of infinity, just in second order system response, just to substitute in place of t infinity. So 1 minus e power of infinity in place of t is infinity minus zeta omega n into infinity is nothing but minus infinity divided by under root 1 minus zeta square sine of omega dt plus theta is equals to 1 minus 0. See here, peak value. So that is this value is going to be what? E power of minus zeta. So e power of minus zeta is simply I am going to e power of minus infinity is nothing but 0. So that's why 1 minus 0. So 1 minus 0 into Sin theta is, this value is going to be 0. 0 into sin theta is 0. So that is equals to 1. That is equals to 1 for at t equals to infinity. So t of infinity is equals to, or c of infinity is equals to 1. Next here, at t equals to tp condition, at t equals to tp, c of t equals to c of tp equals to 1 minus e power of minus zeta omega n tp. In place of t, just substitute the tp, and here tp is nothing but infinity sin infinity. Here 0 into something value is always is 0, so directly 1 minus 0, so 1. From this equation, just substitute in place of t, just to tp, and write here 1 minus this term and sin this term. Already we know that tp equals to what? Peak time, right? So peak time is nothing but 5 by omega d. Our formula is 5 by omega d. Just substitute tp equals to 5 by omega d. E power of minus zeta omega n in place of 5, tp 5 by omega d divided by under root 1 minus zeta square sine of omega d 5 by omega d. Here see, already omega d is there, tp plus y by omega d both cancel, sine of 5 plus theta 1 minus e power. Here what we are getting, 1 minus e power of minus zeta omega n 5 by omega d divided by under root 1 minus zeta square into sine of 5 plus theta, sine of 5 plus theta, 180 plus theta. So here see, observe, sine of 5 plus theta, sine of 5 plus theta is nothing but what? Here we know that peak time is 5 by omega d, and where this damped frequency oscillation omega d equals to omega n under root 1 minus zeta square, and also sine of 5 plus theta equals to, or sine of 180 plus theta equals to minus sin theta, minus sin theta. So all this we know already. So for that, just here at t equals to cp, c of tp equals to 1 minus e power of minus zeta omega n 5 by omega n into under root 1 minus zeta square. In place of omega d, in place of omega d, here omega d is there, so in place of omega d, just substitute omega n into under root 1 minus zeta square. So omega n both are get cancelled, minus zeta 5 by under root 1 minus zeta square, and here sine of 5 plus theta under root 1 minus zeta square. Sine of 5 plus theta is nothing but minus sin theta. So minus sin theta, minus and minus both are plus, so 1 place. Finally, in place of this value, we are going to write the minus sin theta. So minus into minus both are places. So e power of minus zeta 5 by under root 1 minus zeta square divided by the root 1 minus zeta square into sin theta. Okay, this is about the c of tp, c of tp, right? Next, we know that by constructing right angle triangle, the sin theta equals to under root 1 minus zeta square. So for that, here see, sin theta I am going to write the under root 1 minus zeta square. So in place of, here observe, under root 1 minus zeta square. Now this term and this term both cancel. Finally, we are going to get the c of tp is equals to 1 plus e power of minus zeta 5 by under root 1 minus zeta square. This is c of tp equals to this value. We know that c of tp equals to this, and c of infinity equals to 1. Now these two I am going to substitute in the percentage peak overshoot or peak overshoot formula. We know that c of tp minus c of infinity divided by c of infinity. We know that c of tp equals to 1 plus e power of minus zeta 5 by under root 1 minus zeta square. Next here, infinity value is 1, so divided by infinity also 1 into 100. So finally we are going to 1 plus 1 minus plus minus just 0 value, so e power of minus zeta 5 by under root 1 minus zeta square into 100. This is the percentage peak overshoot or maximum peak overshoot. Okay, this is the very important formula. Okay, percentage peak overshoot or percentage peak e power of minus zeta 5 by under root 1 minus zeta square into 100. This is about the maximum peak overshoot. Next, coming to the just what we follow this procedure for the calculation of the peak overshoot, maximum peak overshoot. Simply we consider the definition and we need to substitute t plus tp and we need to substitute co t equals to infinity of that 2 t equals to tp, t equals to infinity in the second order underdamped response of the equation. By that solving we are going to get the two equations. Just substitute again in this formula. Finally we are get the this maximum peak overshoot or peak overshoot, that is e power of minus zeta 5 by under root 1 minus zeta square into 100. This is the important formula, right? Next, see, derive the expression of the settling time. Derive the expression of the settling time t suffix s. Now again we are going to also consider the underdamped second order system. Underdamped second order system for the unit step response. From that we have a see here that unit step response. Just simply I am going to write here, or c of t equals to 1 minus e power of minus zeta 5 by under root 1 minus zeta square sine of omega dt plus zeta. Okay, see here, same this equation. This is e power of 1 minus e power of minus zeta omega n t divided by under root 1 minus zeta square, like that one. Okay, minus zeta 5, sorry, wait, minus zeta omega n t divided by under root 1 minus zeta square. That's one. So from this, just observe this one is the exponential term and here one more is the sinusoidal function, right? Two functions are there. The response of the second order system has two components. One is the decaying exponential component, that is e power of minus zeta omega n t divided by under root 1 minus zeta square. This is the exponential component. Next is sinusoidal component, that is sine of omega dt plus theta, This is the sinusoidal component. From this, just settling time means it is the response to reach the some specified error, right? Specified error. So specified error is here directly. This that is the decaying exponential term, reduces the oscillations produced by this sinusoidal component. When the sinusoidal component produces any errors, any oscillations, that oscillations are going to be reduced by using the exponential decaying term or exponential component, right? So for that we are going to calculate the settling time. Just we are going to consider the exponential component only, because of the exponential component is reducing the oscillations by produced by the sinusoidal signal or sinusoidal component, right? So that's why here the settling time is decided by to calculate that considered as exponential component. The settling time can be found out by equating exponential component to percentage tolerance errors, because of we have a two allowable error or tolerable errors are available in a settling time. So for that we are going to calculate the settling time by equating that exponential component to the that respected tolerance error or percentage tolerance error. Now see the first error here 2%. For that we are going to calculate the settling time for 2% tolerance error band at t equals to ts. At t equals to ts, just we are going to consider exponential component only. That is exponential component what here, minus zeta omega n minus zeta omega n ts divided by under root 1 minus zeta square, under root 1 minus zeta square. So here this is equating to percentage of tolerance. So 2 percentage nothing but here what, 2 divided by 100, that is nothing but what here 0.02, 0.02, that is here I am writing, right? T equals to ts here e power of minus zeta omega n ts divided by under root 1 minus zeta square equating to 0.02. For least value of zeta, for least value of zeta is nothing but here in denominator part, see observe 1 minus zeta. So zeta value is less than 1. So less than 1 means it is the least value or less value of this 1. So I am going to neglecting this zeta value. Directly I am going to write e power of minus zeta omega n t s equals to 0.02. 0.02. Now I am going to apply the or taking the logarithmic function or taking natural logarithmic, we get a natural logarithmic, that is natural logarithmic apply for this equation directly here minus zeta omega n ts and equals to natural logarithm ln of 0.02, ln of 0.02. Here logarithmic of 0.02 log of 0.02 minus zeta omega n ts equals to minus 4, equals to minus 4. So here minus minus both are get cancelled. So further ts equals to 4 divided by zeta omega n, ts equals to 4 by zeta omega n. See here this one, by this solving we are going to log function of 0.02 is nothing but minus 4. Here minus minus both get cancelled, zeta omega and ts. Here ts equals to this, ts is the settling time. Next here where 1 by zeta omega n is nothing but the time constant, where t equals to 1 by zeta omega n. So that is directly I am going to write here in this term t s equals to 4 into t, 4t, where t is the time constant. Time constant is nothing but what, it is time taken for the response to reach 63 point or 63%, 63.02 percentage, like okay 63.02 percentage up to here. So ts is nothing but here 4t, or this t is nothing but the time constant, already I explained in previous classes, right? So ts equals to 4t. Next for the 2% tolerance, the settling time, finally we are going to get the 4t or 1 by zeta omega n, 1 by zeta omega n. This is the settling time for the 2% of tolerable error, right? Next coming to the next error, for consider the 5% of error, tolerable error. For that the settling time, just we are going to consider the settling time here e power of minus zeta omega n ts divided by under root 1 minus zeta square exponential term is equating to percentage of the tolerable. So percentage is here 5%. So 5% is nothing but 5 divided by 100, that is nothing but 0.05, 0.05. So here see in this denominator function, denominator here under root 1 minus zeta square is there. So zeta is value, so here also same thing, zeta square is less than 1, right? So here also zeta square is or zeta is very much less than, very much less than 1, very much less than 1 means it is the lower value, or it is going to be neglecting that. So 0 value near to, so 1 minus 0 under root 1 is directly, it is going to be 1, or it is directly e power of minus zeta omega ts equals to 0.02. E power of minus zeta omega n ts equals to 0.05, 0.05 for 5%. So now I am going to apply the natural logarithmic, or taking the natural logarithmic, we get here minus zeta omega, here log function ln of e power of minus zeta omega, simply ln of e power of minus zeta omega n ts is equals to 0.05. So that's value directly here going to consider as zeta, just exponential is directly coming to the here minus zeta omega n ts equals to ln of 0.05, ln of 0.05 simply. So so logarithmic of 0.05 is nothing but minus 5, sorry, minus 3 is nothing but minus 3. So here minus minus both cancel, so zeta omega n ts, where ts equals to 3 divided by zeta omega n, zeta omega n, that is nothing but we know the time constant t equals to 1 by zeta omega n, 1 by zeta omega n, that is nothing but here 3t, it is equals to 3t. Here just see, observe, see here minus minus both cancel, zeta omega n ts equals to 3, here ts equals to 3 by zeta omega n, where settling time ts equals to 3 by zeta omega n, or t time constant 1 by zeta omega n, that is 3t for the 5% of tolerable error. This is the settling time for two errors, 2% and 5%. These formulas are so very very important for the gate as well as here in your exams. Oh, all these, for any competitive exams, all these formulas are very very important, right? So that's why you can remember all the formulas of time domain specifications. The basic response just we consider for the all the time domain specifications expressions, that is the second order closed loop system for second order underdamped second order system for unit step input, that is the response of t equals to just we write 1 minus e power of minus zeta omega n ts or t divided by under 1 minus zeta square into sine of omega dt plus theta, that is from that we are consider. Okay, this is about the how to solve the, or how to derive the expressions of the all the time domain specifications, like settling time as well as the maximum overshoot or peak overshoot, right? So I hope you understood every expression, how to solve or how to derive. I think all these are easy for you. Next class we are going to solve some problems also. Okay, I hope you understand every point. I think you can remember, or you can remember all the formulas for the time domain specifications. Okay, thank you all.